a pivotal turning point that showed general relativity was correct occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed near the sun. According to the theory, the sun's enormous mass would cause the starlight to bend slightly. During the eclipse, the observations precisely matched Einstein's predictions, establishing the validity of the theory. Just as motion can alter our experience of time according to special relativity, gravity also affects time. Where gravity is extremely strong, time moves more slowly compared to areas with weaker gravity. For example, if you were standing near a massive object like a black hole, your clock would tick more slowly than one place far away from this immense mass. General relativity introduces black holes, regions where gravity is so intense that nothing, not even light, can escape the boundary around a black hole. Is known as the event horizon, which acts as a point of no return. Once something crosses this threshold, it is pulled into the black hole with no chance of escape. Einstein's theory of general relativity has profound implications for how the universe is structured. Initially, Einstein added something called a cosmological constant to his equations because he believed the universe was static. However, when it was discovered that the universe is expanding, he called this addition a serious mistake. This idea of an expanding universe based on general relativity became a cornerstone of the Big Bang Theory, which explains how the universe began. Another significant concept from general relativity is gravitational waves, ripples in the fabric of space-time caused by massive objects in motion, such as when black holes or neutron stars merge. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory LIGO directly detected gravitational waves, further confirming Einstein's theory. Over time, scientists have conducted numerous experiments to test the validity of general relativity, from observing how planets move to the bending of starlight to the detection of gravitational waves. The theory has consistently been supported by evidence. While saying gravity isn't real might sound surprising, particularly since we all experience it daily in physics, it's common to question and explore established ideas. Some scientists like Brian Cox have proposed alternative views of fundamental forces like gravity. One theory challenging conventional gravity is called modified Newtonian dynamics. Emmett suggests that gravity behaves differently at slow speeds, particularly in galaxies, without requiring dark matter instead of adding invisible matter. Man proposes that gravity becomes stronger at low velocities. The gravity debate also involves the mysterious dark matter and dark energy introduced to explain certain phenomena in space. Critics argue that these are unnecessary and that alternative theories can explain the observations. The quest for a deeper understanding of gravity is ongoing, with some scientists believing we may eventually find a new framework to replace traditional ideas about gravity. Time, too, is a layered puzzle in physics. Our understanding evolves with new ideas and evidence. With Brian Cox's latest theory on time, we might be on the verge of a breakthrough that changes everything we thought we knew about the universe. As we delve deeper into time and gravity, we face new frontiers. Recent advancements like quantum mechanics and the search for a unified theory of everything bring us closer to unraveling the universe's deepest mysteries. Quantum mechanics, for instance, deals with the smallest particles in existence and operates in a realm where probabilities, not certainties, govern. This microscopic world behaves differently from the macroscopic universe we observe, where Newton's laws and Einstein's relativity offer predictable understandings of motion. Quantum mechanics and general relativity have long been treated as separate Domains, one explaining the microscopic world, the other the grand cosmic scale. However, scientists are on a quest to unite them into a single framework that explains both the very large and the very small. Such a theory could reconcile the nature of time on a cosmic scale with a strange, unpredictable behavior of particles at the quantum level. The renowned physicist Stephen Hawking spent much of his career exploring these questions, attempting to unify these two schools of thought. His work, alongside that of others, has opened up exciting possibilities, though a complete theory of everything remains elusive. The interplay of time, space, and gravity is also significantly influenced by technological advancements. Instruments like the Hubble Space Telescope and more recently the James Webb Space Telescope have allowed us to peer deeper into space than ever before, observing galaxies that formed billions of years ago and studying how light and time behave at these extreme distances provide valuable insights into the evolution of the universe itself. In addition to observational tools, experiments at the cutting edge of physics, such as those conducted at the Large Hadron Collider LHC, help us test these ideas at fundamental levels by smashing particles at nearly the speed of light. The LHC allows us to investigate the basic forces and particles that make up our universe. This could lead to new discoveries about how gravity works at quantum scales or how time behaves at these extreme energies. The study of black holes and the behavior of time near these enigmatic objects continues to provide new insights into the fabric of space-time. The first ever photograph of a black hole captured by the Event Horizon Telescope in 2019 marked a groundbreaking moment in modern science. Such discoveries challenge our understanding of time, space, and gravity, forcing us to confront the limitations of our knowledge in daily life. The effects of relativity are so small that they are imperceptible. However, on larger scales near black holes or when traveling at near light speeds, these effects become significant as we push the boundaries of space exploration, studying phenomena like the expansion of the universe, the possibility of time travel, or the behavior of gravity at extreme scales. We may one day uncover new laws of physics that fundamentally alter our conception of the universe. One of the most intriguing ideas that continues to captivate scientists is time travel. While often relegated to science fiction, the science behind time travel is rooted in the theories of relativity under certain conditions, such as the presence of a massive rotating object or the bending of space-time around a black hole. Theoretical physicists have proposed scenarios where time loops or curves could exist, allowing for travel backward or forward in time. However, these remain speculative, and many paradoxes arise when grappling with such possibilities. Newton's understanding of gravity was sufficient to enable humanity to travel from Earth to the moon, but as we contemplate the ticking hands of time, we must wonder if our current understanding is just the tip of the iceberg. Could Brian Cox's discoveries unlock the door to deeper truths about the universe? His groundbreaking theory on time may challenge our traditional understanding and lead to profound implications for our perception of reality. Einstein's first major breakthrough was special relativity, introduced in 1905. This theory revolutionized how we think about space and time, establishing that they are not absolute but interconnected in a four-dimensional continuum called space-time. Special relativity showed that time slows down and distances contract for objects moving at speeds close to the speed of light relative to an observer. This concept was elegantly summarized by the equation which demonstrated the equivalence of mass and energy. 10 years later, in 1915, Einstein expanded these ideas with his theory of general relativity, which provided a new understanding of gravity instead of being a force between masses as Newton had described gravity, was revealed as the warping of space-time caused by massive objects. The more massive an object, the greater its distortion of space-time, and this curvature directs the motion of other objects. For example, the Earth orbits the Sun not because it is pulled by a force, but because the Sun's immense mass curves space-time around it, creating a path that the Earth follows. This profound reimagining of gravity was validated through experiments like the 1919 solar eclipse, which showed starlight bending as it passed near the Sun, perfectly aligning with Einstein's predictions. As remarkable as general relativity is, it isn't the end of the story. Einstein's theories describe the universe on the largest scales, galaxies, black holes, and the cosmos itself, but they struggle to explain phenomena on the smallest scales governed by quantum mechanics. Bridging the gap between general relativity and quantum mechanics has become one of the greatest challenges in modern physics. The quest for a unified theory. Scientists are working toward a theory of everything which would unify the laws of physics into a single framework. One promising avenue is string theory, which suggests that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings. These strings exist in higher dimensions beyond the familiar 3 dimensions of space and one of time, and their vibrations give rise to the particles and forces we observe. Another contender is loop quantum gravity, which attempts to quantize space-time itself. According to this theory, space-time is not smooth and continuous, but made up of discrete chunks at the smallest scales. Both theories aim to reconcile the seemingly incompatible worlds of quantum mechanics and general relativity, but neither has been conclusively proven. Time, the final frontier. Time remains one of the most mysterious aspects of our universe. While Einstein showed that time is relative, slowing down in strong gravitational fields or at high speeds is fundamental, nature remains elusive. Is time a physical entity like space, or is it an emergent property arising from deeper laws of physics? Brian Cox's new theory on time suggests that our current understanding may be incomplete. Building on Einstein's work and incorporating recent advances in quantum mechanics, Cox explores how time might behave under extreme conditions. For instance, near the singularity of a black hole, where space-time curvature becomes infinite, the very concept of time may break down. Moreover, the flow of time as we perceive it, the progression from past to future, could be an illusion. Some physicists propose that all moments in time exist simultaneously in a block universe where the distinction between past, present, and future is a matter of perspective rather than reality. Implications for the universe. Understanding time at a deeper level could have profound implications for how we view reality. If time is not a fundamental property, but an emergent one, it might suggest that our universe is part of a larger multiverse where different regions experience time or its absence in vastly different ways. Similarly, new insights into gravity and time could revolutionize our approach to space exploration. Concepts like wormholes, hypothetical shortcuts through space-time, may one day allow humans to travel vast cosmic distances or even journey into the past or future. While these ideas remain speculative, they underscore the need to keep questioning and exploring as technology advances. Tools like the James Webb Space Telescope, the Event Horizon Telescope, and particle accelerators like the LHC will continue to provide data that challenge our understanding and push the boundaries of what is possible. A new era of discovery. Einstein's theories reshaped the 20th century, but the 21st century may bring even more transformative discoveries. From the nature of dark matter and dark energy to the mysteries of black holes and the fabric of space-time itself, science is on the brink of a new era. Brian Cox's work reminds us that physics is not just about solving equations, it's about expanding our perspective on the universe and our place within it. The more we learn, the more we realize how much we have yet to understand as we venture further into the unknown. One thing is certain: the journey to unravel the mysteries of time, space, and gravity will continue to inspire and challenge humanity for generations to come. The unique hypothesis of relativity, distributed in 1905, changed how we interpret existence in basic terms. It tells us that the laws of physics remain the same for all observers who aren't accelerating no matter their motion. This hypothesis introduces the concept of relativistic effects, including the renowned idea that time can expand or slow down under certain conditions. One captivating thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, nearly at the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors positioned perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers, so the light beam should appear to travel a diagonal path. Here's the fascinating part: the time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. Yet, since the path account for time in a unique way to make precise predictions and measurements, Albert Einstein introduced the special theory of relativity in 1905, revolutionizing how we see the universe, particularly regarding time and motion. This theory challenges our intuitive understanding. It states that the rules of physics are the same for everyone, regardless of whether they are stationary or moving. This is different from our everyday experience, where we might assume that if something is already moving and we add more speed, it simply gets faster. However, Einstein's theory asserts there's a maximum speed. Nothing can go faster than the speed of light. In this framework, events that appear simultaneous to one observer may not seem so to someone moving close to the speed of light. Another result of this extraordinary perspective is length contraction. This means that if something is moving, it appears shorter in the direction of motion when viewed from a stationary perspective. And then there's the famous equation ELMC(2), which demonstrates that energy and mass are interchangeable. This is critical for understanding how small particles behave at high speeds and explains processes like nuclear reactions where atoms split. In reality, special relativity isn't just a theoretical idea, it's applied in everyday technologies like GPS. Satellites, for instance, move at high speeds, and due to this motion, time behaves slightly differently for them. If we didn't account for this time dilation effect, GPS navigation would be inaccurate. Special relativity teaches us that time isn't uniform everywhere. It depends on motion. This concept challenges our understanding of reality, suggesting that our normal view of the universe is slightly flawed. According to the special theory of relativity, time isn't fixed, it's influenced by motion. Some fundamental ideas like the constant speed of light and the relationship between energy and mass have been validated by countless experiments, but there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory delves deeper into the relationship between gravity and the structure of the universe. It redefines the old idea of gravity as just a force that pulls things from a distance. Instead, it shows that gravity arises because space and time are curved or warped. It's like saying gravity isn't a mysterious force, it's simply the natural movement of objects in the universe. According to Brian Cox's understanding, General relativity involves thinking of the universe as a four-dimensional structure combining three dimensions of space and one of time. In this framework, large objects like stars, planets, and even us affect the shape of space-time around them. This shaping is what we experience as gravity. Imagine space-time as a stretchy fabric. When something heavy like Earth is placed on it, it creates a dent. If you place a smaller object like a ball near Earth, it moves toward the dent. This mirrors how gravity works. General relativity provides a powerful explanation for how objects move in our solar system, such as planets orbiting the sun. It accurately predicts the paths planets follow, including Earth's elliptical orbit. This understanding differs from the old idea of gravity as a pulling force which struggled to explain planetary motion. The groundbreaking idea is that space-time is curved like a bendy fabric, and this better aligns with what we observe